Controller series. In this video we'll look at our first game. Well, almost a game. So what we're going to do is we're going to use our block draw commands to draw some blocky graphics. So to start off with, we're going to draw a frame boundary. So in this kind of ASCII representation, we're going to draw a 2-pixel boundary around the edge of the screen. Then we're going to have a 4x4 pixel ball that will bounce off those edges around the screen. So a Pong style game without any bats, just a free bouncing ball. So we first define the position of our ball at the start of the game. So I'm going to place it 20 pixels from the left edge and 60 pixels down. So it gives me an X and Y position, as you can see here. Then we need to draw our screen boundary, and there's different ways of doing that. One, we could draw the individual blocks that make up each of these edges. So we could draw 4 rectangular blocks. But a quick way of doing it is to draw the whole screen red using the clear screen macro, which initializes all the screen pixels to the red color. And then within that, we can draw a black box with an offset, as you can see here. So starting in the top left corner at pixel position 2, so row 2, column 2, and drawing it all the way down to row 117, column 157. As indicated here in this diagram. And then we just have a simple main loop, as you can see here. So we have a subroutine that will draw the position of the ball and update its position, moving its XY position. And also in this subroutine, there's some functionality that detects if it has hit the top, bottom, or left and right boundaries. And if it has, it changes the direction of the ball. Then we have a delay. So this will determine how quickly the ball moves across the screen. A delay of 1 is as fast as we can go. A delay of 50 is more usable. After the delay has finished, we then clear the ball positions. So we set the ball positions color to black, and then we repeat. So if you look at the game logic subroutines, so we've got the move ball and clear ball subroutines. So our ball is a 4 pixel by 4 pixel square. We need to remember obviously its XY positions. So we have the variables ball X and ball Y, but we also need to know the direction of the ball. We need to remember what direction the ball is moving across the screen. And this is defined by dir X and dir Y. So if direction X is a 0, it will move to the right. If direction X is a 1, it will move to the left. If direction Y is a 0, it will move down the screen. And if direction Y is a 1, it will move up the screen. So in each frame, we either increment or decrement the ball's position, depending on if it's hit one of those edge boundaries. So to do that, we use a subtract instruction, as you can see here. So we load into a register the ball's X or Y position and then compare it to a limit. And if it generates a carry, then we know we haven't reached that limit yet and we don't need to change the direction of the ball. So for this first test, we load into register RA the ball's X position, and we load into register RB the right limit. And the right limit is defined as a macro. If you go and look at the macro file, you can see that's the value 155. So we then do that subtraction, and obviously if the ball is position 20 and the limit is 155, so 20 minus 155 will generate a negative result, and then we'll jump over the changing of direction. Obviously when the ball does equal 155, then we do need to change direction, so that will generate a 0 result, and this jump won't happen, and then we will update the direction to a different direction such that the ball moves away from that edge. So we do that for all our edges on our screens. So we do it for the right, the left, the top and the bottom, updating direction X and direction Y variables as required. Once we've done that, we then need to update the ball's position. So we look at those direction variables, see if they're set to a 1 or a 0, and we'll either add 1 to the ball's position or subtract 1 from the ball's position. And we do that for the X and the Y directions. So here we're updating the ball's X position, and here we'll be updating the ball's Y position. So the ball will move diagonally across the screen and change direction every time it hits a boundary. Once we've updated the position, we then call the draw ball subroutine, and that just draws a block on the screen 4 pixels by 4 pixels using the draw block command we discussed previously. In addition to our draw ball subroutine, we've also got clear ball, and that does exactly the same. The only difference is that it sets the color to black. So this is our first simple game, I guess a 0-player game in this sense. It's a bit of a screensaver, basically the ball bouncing around the display. So as always, some slightly out of focus screenshots of this. So this is the initial starting screen. So we have our 2-pixel wide outer edge, which we have set to the color red. So that's our display boundary. And we have our 4x4 green pixels at positions row 60, column 20. So to see this game in action, I tried to record a video of the screen. Really do need some sort of VJ frame capture card. That will make my life so much easier, but we have what we have. So for this initial version of the game, the sleep command was set to 50, which is roughly 0.1 seconds between updates. Obviously, you also have the delay associated with the game logic as well, which will slow down the frame rate of our game. I guess that's not to be confused with the frame rate of the video display's controller. From memory, I think it's around about 60 hertz that hardware is running at. So we're updating the frame buffer at a lot lower speed. So the user will see multiple frames of the ball in the same position effectively. We can also increase the speeds. So I have now set the sleep delay to the value 5, and you can see the speed here significantly increased, 10 times faster effectively. And that's probably as fast as I would go with this particular game. You can still see the ball quite clearly, a little bit of a trailing artifact. You don't tend to see that particularly when you're looking at it just as a human eye. Obviously, we've got slight artifacts associated with the video recording process on the camera here. So you quite see that trail that you're seeing on the video here in real life. Obviously, you can make it faster. So we can reduce the delay now down to the value 1. And as you can see, that one is whizzing across the screen quite frantically. And if you look closer, you can start to see some artifacts here. So we're updating the screen faster than the video display controller can draw the screen. So if I pause that one, again, we've got some artifacts here of the video recording process. But if I go look here, here's one, for example. So here we've got 2 balls. So the video display controller, I'm guessing, has updated the screen and drawn the first ball, and then I'm coming in as it's drawing the first ball and write the second ball to the frame buffer before I delete the first ball. So the ball's position starts to become unsynchronized with the frame buffer. So you really need some sort of mechanism to stop the game writing a new ball position until the ball has been written to the screen. This may be an issue for some of the smaller games where your game logic doesn't take that much time to calculate, so therefore there's a possibility of updating the frame buffer too quickly. But for most complex games, especially of those when you've got lots of tiles to draw and lots of things moving on the screen, this has a significant amount of processing time associated with it. So fundamentally, the game can't perform all the calculations it needs to perform faster than the display can display them. So I think it should be okay. If it isn't, I'll have to add some synchronization commands such that the processor only updates the screen when it's safe to do so within the blanking periods of the video display controller's operation. Alternatively, we could just call it a feature. So in the original Space Invaders game, as you shot more and more of the Space Invaders, the game sped up. And obviously that was nothing to do with any timing calculations. It was just that the hardware could draw the screen faster because it had less to draw. So when you had lots of Space Invaders on the screen was updated slowly. And as you got down to that single Space Invader, that's why he started to zoom across the screen. Nothing to do with game logic, just the speed that the hardware could then update the display because it had less to draw. Another game feature you commonly see in old retro 8-bit games is when you get a flashing screen. Again, you may think, oh, that's sort of showing a different phase of the game or something is happening in the game. But again, it was quite common within games of this era that when you start to see a flashing screen, it was a sign that the program had too much graphical data to display to the user. So if it had tried to display all of the data in one go, game dynamics would slow down, so the game would become non-responsive. So what they would do is they would display half the graphics on one frame, and then on the next frame they'd blank that region and display the other half of the graphics. So it looked like the screen was flashing, because in between frames it would be basically turning those pixels on and off. So I'm not 100% sure if they did do it in Pac-Man, but when Pac-Man eats that energy pill and you can then go around eating the ghost starts flashing. So that reduces the amount of graphical data you need to draw on the screen. So again, would allow the game logic to run more quickly. As you're processing less graphical data, you're doing less work in the program. So hopefully through this simple example of a bouncing ball, you can see how we can take the next step and we can implement a game like Pong, as you can see on the screen here at the moment. So again, all the main game graphics are drawn using the block right command. It's only the scores at the top there are drawn as tiles. So it's simply a case of setting the game boundaries, top and bottom, left and right, and detecting when the ball has hit one of the top or bottom boundaries, so it bounces off it at the right angle, or when it's hit the left or right boundaries, has it hit a bat? Is the ball and the bat in the same position? In which case, again, it would reverse the direction of the ball. Okay, a slightly shorter video than normal, but I wanted to show that you could just use simple block right commands to implement a very simple game. So at the moment I'm just updating the actual hardware board, so actually making the physical SimpleCPU games console. And what I'm looking to do is to create a web page of this hardware, so you can download the configuration file and go through those programming examples, and you can create your own games. Fingers crossed, touch wood, I'll get that uploaded in the next day or two.